like that. I gave you yesterday to look at those solutions from 2.5. Is there anything that you were unsure about? Anything that you want to look at, talk about? One was pretty nice and self-explanatory. The only thing that was weird that came up with number one is you had that rational zero that worked, right? That 1/2. And so like how you choose to write that is kind of up to you. Right? If you just call it minus 1/2, then yeah, you've got the 2x squared minus 18 left over from synthetic division, right? But we try to avoid writing fractions as part of it because my function from the beginning didn't have any fractional coefficients. So I should be able to rewrite it without. And so what I want you to see is like that 2x squared plus 18 has that common factor of 2 that we would really like to take all of this and pull that 2 out and drop it into here instead. And I'm good either way with a of x being written however you want, but we have to realize that if you're going to write it this way, right, that top way, and then you solve it, you're still going to get plus or minus 3i, but you have that common factor of 2 that would then otherwise like have to sit out front. I say, you know what, you got a common factor, it can go somewhere, and let's use that to make those fractions disappear. So kind of pulling the 2 out from here, right, calling it 2 times x squared plus 9, and then allowing that 2 to get multiplied in instead. Because if you left this last line right here as x minus 1/2, you would have to put the 2 up front instead. And that can be hard to remember, and that I would hate for you to lose silly points for getting the 2 because you used the 1/2 and not the 2x minus. Okay. Either way is good. I like the way I wrote it though best, because I don't have to remember anything. Okay. 2 was another kind of interesting one that I really wanted to make sure I said one thing about, but first, Grace. So the 2x squared plus 18, this right here, okay? So that's the same as this, right? 2 times x squared plus 9. So either you put the 2 up front as your leading coefficient, right? Because the leading coefficient of the function itself was 2, so it should always match. And then you're fine like that. Or you say, you know what, this 2 can get multiplied into any of those factors to help me eliminate fractions. And that's what I did from this first line on the right here with a of x down to the second line, is I took that 2 that I recognize as being a common factor, I pulled it out of a factor that it didn't need to be in. I didn't need to make x squared plus 9 twice as big, right? But I would really like to make this twice as big to get rid of those fractions. So that's just a style choice that allows me to avoid, again, the scenario here that would then require that 2 up front. That would be a big. Okay. Does that make sense? Sweet. Okay. Second one, degree 4, so I get 4 zeros, but we only find one actual rational one. And so here's the thought process that I started to have, and I was like saying these things to myself, and I said, you know what, let me just write this stuff down. But think about it. If your degree is 4, and complex zeros always come in conjugate pairs, right? If you've got one complex 0, you've got 2, right? Guaranteed, right? 5i and negative 5i, 2 plus I and 2 minus I. The same thing is true with irrational ones, because they come from that quadratic formula that has the plus or minus some square root in it. So if they're not rational, they can only be irrational or complex, and they're always going to come in pairs. And so if you've got a degree 4, you either have 0 complex zeros, 2 of them, or 4 of them, right? And so if I have one rational 0, could the other 3 be complex? No, because they have to come in pairs. There has to be an even number of these. And so I had that thought. I said, okay, actual rational 0x equals 3. I said, okay, if all complex roots come in conjugate pairs. And the degree of b of x is even. That means I have an even number of complex zeros, which means I need to have an even number of rational. And if I have at least one rational zero, what that tells me is that rational zero had better show up an even number of times. The multiplicity of this rational root has to also be even. And I had that thought that kind of ran through my head, because when I think about finding all of the zeros, I want to deal with the rational one first as best I can. And so that kind of gave me the hint that x equals 3 probably has a multiplicity bigger than 1. Not probably, definitely, right? And so to me, I'm just going to check it twice. And it worked out twice. And how do I know that? Well, I just looked at the graph. But it was kind of a nice, like, little thing to have in the back of my mind that says, all right, should I even bother looking at the graph? And in a case like this, absolutely, right? Absolutely. And it allowed me to say, all right, I can do synthetic division twice, which means I can pull it out twice, which means I can write the factored version of that factor with a multiplicity of 2, which just allowed me to kind of work through this a little bit quicker. Now, it could have showed up times, right? Show up once, it's got to show up twice. And it could have been like 2 rational ones and 2 complex ones, or 4 and 0, right? But if this is a 1, this could be a 3. That means, right, it's got to be 2 and then 2, or 0 and then 4. Okay, so I kind of had that thought process, and then it kind of worked out nice with the leftover quadratic to, square root of negative 36 was 6i, and it simplified nice and allowed me to just write my factors out. X minus 3 twice, and cool. You want to write it twice? Great. You want to put it just an exponent or 2? I'm cool with that as well. Okay. So I just wanted to make sure I said those things. Okay, 3 and 4 were okay. They gave us the first 2 zeros, so I had to add in the 5i because we had negative 5i, and then write their factors, and then make sure we multiply out the i's, because they said for 3 and 4 to use real coefficients only. Numbers 1 and 2 didn't. They just said factor it. Completely factored, so I want to have my i's left over. But for 3 and 4, they said real coefficients only. So I multiplied the conjugate factors together, and the i's all disappeared. So I'm good here. This first boxed-in version with the x minus 2 and the x squared plus 25, cool. Leave it. I'm good. You want to go further? That's up to you. Totally up to you. That's your choice. It's an opportunity to make mistakes, but it's also an opportunity to see things in standard form, which can be nice. Same thing with 4, but man, that was a lot more work. Like getting myself to z of x here with all the factors versus z of x here written in standard form, a lot of mistakes can be made in those spots. Yeah, question? Like 5xi versus 5ix. I'm not super picky about that. I like to put my i's at the end. But writing 5ix, you're putting your coefficients first, and then your x at the end. That's cool too. So I think that's up to you. Your style. But just be consistent. Whatever you decide to do, stick with that. But I'm good either way. But you're probably going to put the i's at the end. Yeah. Good question. Okay, but it multiplied out nicely, and life was good, and we got ourselves to there. Cool. Sweet. All right, let's do this thing. Let's start the beginning of the end. Okay, I'm going to stop sharing here for just a moment so people can start focusing on me writing up at the front. But what I'm eventually going to be doing is getting myself into my graphing calculator to look at some stuff. So you're probably going to want to have that out nearby. And then so folks at home, whenever I jump back on to the other one, you know what? I wonder if I could do that. I wonder if I could just keep sharing that one, but pin me on the actual camera. Let's try. Let's present me right here. I'm going to go to the calculator. But on the meet itself, let's see if this works. I'm going to pin me and Delaney as a bonus. I'm going to turn those lights off. All right, let's do it. 2.6 and kinda 2.7 together because they're both talking rational functions. Now, realistically, we're not even going to finish 2.6 today, but I want you to realize that I'm just going to lump everything all together into kind of one last big section, calling them rational functions, because 2.6 does one thing for rational functions, 2.7 does something else. It's all to get us to the same end goal. And that end goal is to be given a rational function and graph it by hand completely. Okay, as best we can. Now, it'll still be a sketch, but we're going to break out the straight edges and we're going to graph paper, we're going to do this thing right. Okay? But the way that I'm going to try to design my notes, which is going to be a little bit of a pain for people at home because I'm going to keep moving the camera back and forth. This board is going to be 2 examples and kind of the answers that we get from the questions I'm asking. This one over here will kind of be the in general. Like, here are the notes that get us to the kind of solutions. Okay, so I'm going to jump back and forth a little bit. So I will try to talk my way through it so everybody at home hears what I'm talking about. But let's start by making it up. And I'm going to start simple because I know that rational functions are in general basically brand new to everybody. So I want to start with a simple rational function. So I'm just going to call it f of x. And what I'm going to do to make a rational function, rational ratio, fraction. All of our rational functions will be fractions. And those fractions will be one polynomial over another. Okay, but the denominator needs to be at least linear to make it worth looking at. Because otherwise, if it's just a constant, then I just divide and it's the polynomial over again. So I'm going to put a linear polynomial on top, call it x plus 3, and a linear one on the bottom. How about x minus 2? Okay. But in general, come with me for a moment. What we're talking about with polynomial on top and a polynomial on bottom, I want to just give those a name to make it easier. So I'm going to call the top one always n of x for numerator and the bottom one d of x for denominator. But I'm going to use capital letters because it's not a specific function. It's kind of just, in general, I want to be able to say, here's what's going on with n of x, and here's what's going on with d of x, okay? But both of them, so n of x and d of x, are polynomials. And we know basically everything there is to know about polynomial functions, and we're going to use all that knowledge to make as much sense of these as we possibly can. Okay? But when we start with rational functions, it's a little bit different than how we started with polynomials. With polynomials, we found all of the important points, right? We found the x-intercept, the y-intercept, we figured out what the end behavior looked like, and then we just graphed it, right? With rational functions, what we start to see with these like polynomial denominators, we've got x's at the bottom. That might cause some issues for us in plugging in any number we want. Right, because polynomials, domain, everything, right? Negative infinity to infinity, all real numbers, because all I'm doing is plugging in an x value. I'm raising it to some powers, multiplying it by some numbers, and then adding them all together, right? I can do that with anything I want. But now that we're dividing potentially by x's, what we see is that there are going to be some values of x that don't produce a y value when we plug it in. Right? What we have that we want to kind of start with is we want to think about what values of x to exclude. Excluded values of the domain. And so instead of starting with all of the points that do work, let's start with the ones that don't. Let's think about like x being not equal to a small collection of numbers. And it could be none of them. It could be 1 or 2 or 3, probably at the most for us here at a pre-calc level, of numbers that just cause a problem for us that we can't plug in because it would give us an issue trying to get a y value back. And so, like, what's the problem? When you think about, and you can just look back at the original function itself, a value or values of x that don't work because it does something that we know we can't do with fractions. What are we not allowed to do, Evelyn? We can't divide by 0, right? We can't do that. And so when we think about excluded values of the domain, the only ones that give us issues are zeros of the denominator, the zeros of d of x. Okay, this is just going to be x equals some set of numbers, and it might just be 1 or 2 or 3, right? That are all those zeros of dx. And that's how we'll do it, okay? And so we just want to avoid those. But what I want to kind of look at is what does that do graphically? Because obviously there's not going to be a point there. I can't put a point at that spot. I can't put a dot. I have to do something else. So like the graphical consequences, I guess, I don't know, of plugging in numbers that we know we can't plug in. Okay, and what you're going to see is that there's more than one possibility, and we're just going to start with one first. Okay, and so I'm going to go back to this graphing calculator, and so folks at home, if you want to pin my shared screen so you can see it a little bit bigger, I'm just going to go in and I'm going to plug in this function. Okay, so I'm going to go to y equals and I'm going to type it in, but be careful typing it in, right? If you have a denominator and a numerator in both of these cases that's more than just a monomial, you need parentheses around everything. Because if I just type it like this, the only thing being divided right now is 3 over x, right? That would be x, no fraction, plus no fraction, the fraction 3 over x, right? That's, for those of us in class, you can see this a little bit. That's that, right? X plus 3 over x minus 2. That and that are definitely not the same. Okay, so I want to make sure that I drop parentheses around it. And you can go back and clear it and just type in your parentheses, or I don't know if I've said this to you before, but if you make a mistake that you don't want to make everything disappear and you just want to insert something, like right now, if I just type parentheses, it replaces the x, and that's no good. I want to just like slide all of this over and put a parentheses there. I want to insert, so second delete. Watch what happens. It goes from a blinking black box to just a blinking x. And when I type the parentheses, it will slide it all over instead of replacing it. Now, I have to do it again, like right here, I have to insert a parentheses, and right here, I have to insert, like it might have just been as much work to just retype the whole thing, but maybe if you just make one little tiny mistake, sometimes insert can be really nice. Okay, cool. I'm going to always, when I start, I usually zoom standard, so zoom number 6, to get me to a negative 10 to 10, negative 10 to 10 kind of window, but I'm squishing a square into a rectangle, so I'm kind of stretching out the x-axis, which isn't good. So I am going to zoom square, zoom number 5, to make the x and the y tick marks evenly separated. But take a look at what's happening at x equals 2. Because what's the excluded value from this function? 2, right? Because when I look at like the only problem with f of x, when I think about like trying to write down these excluded values, is me saying, you know what, x had just better not be 2. So if I drop in 2, I'm going to get 5 over 0, and I know I can't divide by 0. But what does that do graphically? Well, clearly there's no point there for sure. But something else is happening at that spot, but it's invisible. But we're going to draw it. There's an asymptote at that spot, right? We have this line. The graph is going to approach, but not actually reach. And so everybody at home can see it. I'm going to graph that. Oh, but it's y equals. Fudge, I can't do it. I got to draw it out by hand. Yeah, I got to draw it out by hand. So what I'm going to do, folks at home, is I'm going to draw a vertical line at x equals 2. But because that's not actually part of the graph, I'm not going to leave it solid like that. I'm going to dash it. I'm going to dot that line. So it's more of a guide for us to see what happens. okay? So the graphical consequences, what might happen at some of these excluded values is we might have a vertical asymptote, okay? And an asymptote is a line, that's the letter A, a line that, that a graph approaches but never reaches. All right, and so as we get closer and closer and closer to x being actually equal to 2, what we see is that the blue graph itself, right, gets closer and closer and closer to that red line, that red dotted line that I drew in on top of this graph, okay? But look where it's headed. Like if you follow the blue graph from the left edge towards what might exist at x equals 2, where is that blue graph going? Is it headed towards a specific y value from the left? Like, what do you think the trend is for that blue curve on that left-hand side as we get closer and closer to that red dotted line? Are we headed towards a number? Well, let's see. Let's look at like actually getting closer to 2, like plugging in 1 and 1.5 and 1.9 and 1.99 and 1.999 and 1.99999. Now, this isn't actually 2. Remember, it can only fit 5 digits, so it had to round, so be careful. And this number is so big in the negative direction, it needed scientific notation to fix that. But what do you see happening to the y values as we get closer and closer and closer to 2? Now, when I actually get there, nothing, right? Error, can't do it. But as we approach that number, as x gets closer and closer to 2, what's happening to those y values? Yeah. Right, so in the negative direction. So careful saying small. Small usually means close to 0. That's negatively really big. It's just going down instead of up, right? So it's getting really big in the negative direction. And that kind of makes sense based on the picture that we saw. Is like as we get closer and closer to 2, like really, really quickly, like boom, takes off, right? And same thing on the right side. And you would see if I plugged in like 3 and 2.5 and 2.1 and 0.01, number would just take off. Y's would get really, really, really big. So here's what's actually happening. Like, here's the better way for me to describe what a vertical asymptote is actually doing, is that as we approach whatever this number is, right? And so like say, like, I don't know, like a 0d of x, call it like x equals some constant, like x equals c, whatever that number is, right? And so for a vertical asymptote, as x like isn't actually equal to c, but as x approaches c, okay, so that arrow means like getting closer and closer and closer and closer to it. Y approaches, right, is heading in a certain direction. Now, it could have been positive from the right, or it could have been negative from the left in this case. But as we get closer and closer to that x value, in this case, x equals 2, where are your y values going? Like down forever or up like forever, right? Because I can get really, 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 really close. 2.1 million zeros and then a 1. And I'd still get a y value back. And it would be humongous. And I could even get closer, and then closer and closer and closer. These things are just going to grow forever, right? Either up forever or down forever. What do we call forever? That's what a vertical asymptote really is that as we approach that x value that we know doesn't exist, our y values used to get really, really, really big, either in the positive or negative direction. And it's just because of what's happening with the fraction. Right? I'll do it over here so people can see it, but don't write this down, but you can just see what I'm talking about. Like if I plug in a number really, really close to 2, my denominator, x minus 2, gets really small, right? 2.000001 minus 2, right? Some super tiny number, right? But if I plug it in up top as well, 2.0001 plus 3, right? Some number, right? Whatever it is, but over something really small, really, really, really small. What happens to like a whole fraction if you take a regular size number, right? But you divide by something super, super tiny. Do you know what the result of fractions is when your denominator is really small? This gets really big, right? You're dividing by 1/1,000,000th. So what are you really doing? Multiplying by 1,000,000. You're taking this numerator and you're making them 1,000,000 times bigger because you're dividing by 1/1,000,000, right? And that's what's happening as we get really close to this number, your denominator gets closer and closer and closer to 0. Now, but can we actually get there? We actually divide by 0? No, of course not, right? I can't divide by 0, which is why we get the error in the calculator. But we have this possibility of that vertical asymptote. And we'll figure out whether we should be going up or going down as we approach it. Well, that'll kind of come with time. But I want you to know why this is really happening. It's because your fraction's denominator is just super, super, super tiny. Cool? Okay. So there we go. If I wanted to, vamos conmigo. If I wanted to, sorry, write down the excluded values, well, it's really just x can't be 2. But if I want to write down the equation for the vertical asymptote, which I will probably never write out the full words of those again, I will always just say VA. That is the equation of the line, that dotted line at that spot. The equation of that line is x equals 2. Okay, so when you list your excluded values, you're really just kind of listing the domain. And you're saying, okay, instead of listing all the numbers that do work, kind of like we did, if you remember in chapter 1, we just said, here's the numbers that don't. That's a much shorter list. Okay, your domain, excluded values, x just can't be 2. But when I list my vertical asymptote, I'm writing the equation of the line that I'm going to kind of use as a guide for me to get closer and closer and closer to. But as I do, we go forever, or down we go forever, but we never actually get there, right? Because I can't plug in 2. Sweet. Okay, let's do another one and kind of have that same conversation about excluded values and what that does graphically. But linear over linear is done. Let's up the ante a little bit. Let's go quadratic on top. So x squared minus 9, and then on bottom, let's go like x squared plus 3x. Quadratic over quadratic, both polynomials. I'm good. So the g of x is definitely rational. But I always want to start by figuring out what values don't work. I want to list those excluded values, the zeros from the denominator. And that's really what your vertical asymptotes are going to be. They're going to be x equals your zeros from the denominator. Okay. D of x, that's why I named it, so I can use it. The zeros from d of x. Okay. So let's do it. Let's kind of come over here and say, all right, if I could just figure out the x values that would make 0 in the denominator, those are going to be my problem spots. Those are the numbers I'll write down. So can you look at that denominator, x squared plus 3x, and figure out, just by looking at it, what numbers would create 0? Definitely 0, right? Because plugging 0 in for x, you get 0 plus 0, and that's 0. Now, it's quadratic, though. It's degree 2, so I'm expecting 2 answers. Now, but that can be kind of tricky to see, right? You probably had to think that through, start dropping in some numbers to see what actually got you to 0. Man, I wish that it looked more like this. I really wish I could just see the individual factors, because then each factor would just have a 0 like we do it for polynomials, and it would be so much easier to pick out -3 rather than having to figure out -3. So if I want to see each of those individual factors, what should we do? Let's factor it. And in fact, that's probably what we'll always start with. You should just factor that denominator to see what we get. And so x squared plus 3x, how should we factor that? Greatest common factor always is a great way to start. So plot the x, I've got the x plus 3 left behind, and wow, that makes it so much easier to see that 0 and -3 are those factors. And I'm so glad you said 0 first, because now they're in the right order. For the order that we list them from, like the factors from left to right, you want to write them literally on the number line from left to right. That's cool too. I don't care either way. And there they are. Those are the only two numbers that are ever going to cause me any problems. And away we go. And we can start thinking about what could create a vertical axis. But instead of just dropping them in and saying x equals 0 and x equals -3, let's look at it. I want you to see what happens. So I'm going to go back to my graphing calculator over here. I'm going to keep this one because I like it. I'm going to save it, but I don't want to look at it. So I'm just going to go to the equal sign, press enter to turn it off, but that saves it in there, which is nice. Okay, x squared minus 9, close parentheses, division, open parentheses, x squared plus 3x. And I'm already in that zoom standard, zoom square window. So I shouldn't have to zoom again. I should be able to just press graph. It'll keep me in the same window. And there it is. Okay, there is on my graphing calculator the graph for g of x. And so look at x equals 0. Does it look like there's kind of that border, like this guide, this indivisible wall, this invisible wall that exists at x equals 0? That as I get closer and closer to it, y just either takes off up or down. So I feel really good about that. I like coming back over to my work and saying, you know what? I believe it. Graph looks good. I definitely have a vertical asymptote at x equals 0. No, I'll come down here. X equals 0. Guaranteed, for sure, looks good. But what about at -3? Do you see a vertical asymptote at -3? So something else is happening there, okay? Now, I still want to feel pretty good about the fact that, I'm just going to delete all these, that at 0 I get an error, and at -3 I get an error. Okay, I did my factoring right. Those are definitely my excluded values. But if I don't have a vertical asymptote at x equals -3, but I'm still getting an error, there's no point there. But doesn't it kind of look like the graph is connected and that there's a point there? Welcome to Zoom Standard. Zoom Standard sucks. It just does. And the problem that we've got is because when you look at the window that we deal with this, the delta x, the trace steps that we take are just not nice numbers. It's so rational. 1295, 1295, 45. I don't know, who knows, man? Like, it's just not nice. And if there was a better window to see a better step to take, we might be able to see something that's happening. And so as much as I don't really think it sucks. That was just for dramatic effect, and I got like half a laugh, so that was good. I always start in Zoom Standard and Zoom Squared out, but there's a better window to see more. It's actually Zoom number 4, Zoom Decimal. And now it'll still center you at 0, so my vertical asymptote that's already drawn in there is really nice, but look at what's happening at -3. And that's literally the word we're going to use. There's a hole at x equals -3. There's a gap at that spot. So it's definitely still missing. But there's just a different graphical consequence at a spot, in this case, like -3, as it compares to what happens at x equals 0. And so what I want to do is kind of talk about that difference that we see when we plug in 0 compared to when we plug in -3. Like, why are we getting a hole at some point, right, at y, right? Vertical asymptote is an equation, right? X equals some number. A hole is it's an ordered pair. It's a coordinate where there's literally a finitely small and infinitesimal hole. Now they draw it humongous, and we're going to do it too. When we sketch these graphs, we're going to make that hole large, so it's super obvious. But really, that hole only exists at -3 comma something. And what does that something kind of look like? What does the y value look like? Looks like 2. And we want to confirm that, though. Okay, but how do we know that there's a hole at that spot? Let's talk about it. Let's go back to the function itself. Okay, and let's look at what happens when we drop in 0, which gave us a vertical asymptote, compared to us dropping in -3, which gave us a hole instead. Right? Way back here, when we dropped in like f of 2, what did we get? What, 5 on top and 0 on bottom, right? That gave us a vertical asymptote. Okay, come back over here, and let's drop in g of 0. Let's see what we get. You plug in 0, obviously the denominator is going to be 0. What happens on top, though? What do you get? -9. Cool. So -9 over 0, 5 over 0. Those give us vertical asymptote. What about dropping in -3? What do you get? Obviously on the bottom, we're going to get 0. But what do you get up top? Also 0. That's what makes it. Okay? Your vertical asymptotes are going to exist when you've just got some number over 0. Okay? As long as that number up top isn't also 0. So when I start writing this stuff down, I can say, okay, woohoo, I must have decked you. That was good. I'm so glad that didn't happen. A vertical asymptote is going to happen when you get like some number over 0, as long as that number isn't 0. Really, when we talk about x being equal to zeros from the denominator, it's zeros from the denominator only. Holes are going to exist at x equals your zeros from both the top and the bottom of both n of x and d of x. Okay, so if you get 5 over 0, 10 over 0, pi over 0, -3 over 0, whatever, 9 over 0, -9 over 0, vertical asymptote. Because my top number is approaching some number and my bottom number is getting super, super tiny, which means my fraction is exploding, going really, really big, really, really quickly. And we're going to get that vertical asymptote. But if we approach 0 over 0, right, we're at 1 over 1, 0.5 over 0.5, 0.1 over 0.1, 0.01 over 0.01. We're just getting closer and closer and closer to 0 over 0. And those numbers are just going to start like shrinking at the same rate, which is why we don't take off and go anywhere else. So I know that I'm at -3 comma something. And it looks like -3 comma 2. But how are we going to find that y value without the graph? Because we don't have that. Right? We just have this. This is all we've got. What do you think we could do to figure out the y value that goes with that point? Because obviously you plug in -3, no good, right? You know, we've got x plus 3 on top and x minus 3 on bottom, right? And so there's that common factor that we see show up. Top and bottom, I just factored the top, folks at home, g of x. Difference of squares, right? So x plus 3, x minus 3, no problem. So don't just factor the denominator. First thing to do, factor everything. Right? Just, we know how to factor. So always a good idea to say, let me just write the factored version of this because it'll help me find my zeros from my denominator. And now zeros from the top too. And if they're the same, That's going to give me a hole instead. But I want to find y. I know that -3 is that spot because I got that after top and bottom. But if I plug it in right now, we just get 0 over 0, and that's no good. What do you think we could do to give us something that we could actually plug -3 into and get that value, hopefully 2, back? God, I love that sound so much. The gears grinding. I love it. Take a look at what I did. Factor everything. X plus 3, x minus 3 on top, and x times x plus 3 on the bottom. What could we do to give us a place to actually drop in -3 and get an answer back? Yeah. Simplify. You have an x plus 3 up top and an x plus 3 on the bottom, and that was the problem, right? That was what was creating 0 over 0. So if we could write the simplified version of this function, now the problem with plugging in -3 is gone. And what you're going to see, which is crazy to think about, is that obviously those have to be different functions, right? Because one was quadratic, one is linear, top and bottom. But look at the difference. What was that? X minus 3 over, and I don't need parentheses now because it's monomial denominator. But look at what happens. Like, watch it. It's going to graph kind of quickly. But we had the pink graph. Look at the black graph that goes right on top. The exact same graph, but it goes through the hole. Because plugging in x minus 3, x equals -3 isn't a problem anymore. I took away the problem by simplifying. So to find that y value, let's make sure we factor and simplify first. Now what do you think we could do? Now that we have the problem away, the plugging in -3 isn't a problem anymore. So what do you think we could do? Like here you've got x minus 3 over x. And you know where your hole starts. -3, comma, something. Plug it in. Because I couldn't plug it in here, -0 over 0. But I can plug in -3 there. Right? Into the simplified version of this x minus 3 over x. I can now drop in -3, and let's see what we get. -6 up top, -3 on the bottom. What's -6 divided by -3? And there's that y value that we thought was that location of the hole, and we were right. So to find y, factor and simplify, then evaluate at x equals whatever, right? Evaluate it at those zeros in the simplified version. Use that almost identical function, and you just drop in whatever those problem spots. And so you might have a vertical asymptote, you might have a hole, you might have both, you might have neither. And you might have 2 vertical asymptotes and 3 holes, or 1 and 4, or 0 and 1, like any combination goes. But the nice part about this is that I only care about real numbers. This is x and y. I'm just graphing the real plane. So if I get imaginary answers, they don't matter to me here in 2.6 and 2.7. I want real results only. Cool. All right, I just want to talk about one one last thing. I have like 1 minute though. That's okay. So those are all the x values that disappear. Okay. I want to talk really quickly, and don't worry, we will pick this up right away next time I see you, not in person, but on Friday when we go remote to talk about this. What do I want to do? Zoom standard, Zoom square, and I want to turn these back on. Okay. Do you notice any y values that are missing from these two functions? Maybe a horizontal asymptote, a line that this graph approaches on the left and on the right, but never actually reaches. X equals 1. And the way to find that, and I'll talk about this again, look at both of these functions from the beginning. What's your degree on top for f of x? 1, right? What's your degree on bottom? Are those the same? And when numbers get really, really humongous, adding 3 to a bajillion won't matter, and adding -2 to it won't matter. What's x divided by x? Y equals 1. What's x squared divided by x squared? Y equals 1. Okay, so we'll get back to that. It's a comparison of degrees. It's a little bit different, but we'll pick up with horizontal asymptotes. Really, just end behavior. The word asymptote is a super loose term because we can cross horizontal asymptotes. You'll see that later. But your work for tomorrow, if you can, I know juniors, you got PSAT tomorrow. So homework 2.6a is out there. It's just 4 problems. Find the vertical asymptotes and holes. That's it. Okay, no horizontal stuff. We obviously haven't gotten far enough in that. If you can do it today or tomorrow, juniors, great. If you're really like worried about PSAT and then really run down after and you need Friday to do it, cool. No big deal, all right? But try to get it done because I want to kind of use this knowledge and pick up right where we left off. So I will see live remote on Friday. See ya. And if you need any help, if you have more questions, say later, Grace. Just let me know. Okay. Anybody at home have any questions? Oh, by the way, if you haven't seen me, my hair is blue. We did it. $500. Nice. You guys all good?
Yep.
Sweet.
Thanks, Mr. Rosinger.
You guys are more than welcome. Happy to. And yeah, so just check the announcement for tomorrow. But really, I can't make juniors do a whole lot, so I don't think I'm going to make everybody else do a whole lot either. So, but check the announcement so you know what's going on. But just work on that homework 2.6a and make sure you're feeling pretty good about it. Just really factoring and plugging stuff. Cool. I'm going to stop recording. And if you guys are good, I will log off as well.
Thanks, Rosie.
Thanks, guys. See ya.